In this recording, we want to look at one-sided limits. One-sided limits are limits as x approaches a number from the right or as x approaches a number from the left. Notice the notation in figure 1.51a. We have the limit as x approaches c, and we have a plus that is a superscript. That means the limit as x approaches c from the right or from the positive direction. So this is the limit as x approaches c from the right of f of x is equal to L. That means as we get closer and closer to c from the right, our y values will get closer and closer to L. Notice in the B part of the figure that there is a negative or a minus sign as a superscript. That's the limit as x approaches c from the left of f of x equals m. That means as we get closer and closer to c from the left, our y values are getting closer and closer to m. Here is an example of a function that has different right-hand and left-hand limits. First, as we think about our function and what happens as we approach 0 from the left, all of our y values to the left of 0 are -1, so as we get closer and closer to 0, our y values are all -1. So the limit as x approaches 0 from the left of x divided by the absolute value of x is -1. As we approach from the right, the limit as x approaches 0 from the right of x divided by the square root of, or x divided by the absolute value of x would be 1, because all of those y values are 1. So you'll notice that these limits are not the same. Here is an example of a function y equals the square root of 4 minus x squared. As we approach 2 from the left, you'll see that our y values approach 0. And as we approach -2 from the right, you'll see that our y values approach 0. However, there is no left-hand limit at -2 since the graph is not defined to the left of -2. And there's no right-hand limit as x approaches +2 because there is no graph. The function is not defined to the right of 2. Now, to say that a function has a limit as x approaches c, the limit from the left of the function and the limit from the right must both be equal to L. So the limit as x approaches c of f of x is equal to L if and only if the limit as x approaches c from the left and from the right of f of x are both equal. Now let's consider this piecewise function, and let's look at some different points along this graph. Let's start by looking at x equals 0. If you'll notice, there is no left-hand limit for x equals 0, since there's no graph to the left of 0. However, there is a limit as x approaches 0 from the right. As x approaches 0 from the right, our y values get closer and closer to 1. So 0 has a right-hand limit, but not a left-hand limit. If we look at 1, the limit as x approaches 1 from the left is 0, and the limit as x approaches 1 from the right is 1. Since the left and right-hand limits are not the same, the limit as x approaches 1 does not exist. Now let's look at x of 2. The limit as x approaches 2 from the left is 1, and the limit as x approaches 2 from the right is also 1. Since these two limits are the same, the limit as x approaches 2 is 1. Now notice that f of 2 is not 1. f of 2 is 2, and that doesn't matter. In order for the limit to exist, the limit from the left and the right have to be the same. Now let's look at x of 3. Notice the limit as x approaches 3 from the left is 2, and the limit as x approaches 3 from the right is 2. Also, f of 3 is 2. As long as the limit as x approaches 3 from the left and right are the same, that limit exists, and the limit as x approaches 3 is 2. Now let's consider x equals 4. The limit as x approaches 4 from the left is 1, even though f of 4 is not 1. Notice though that there's no limit as x approaches 4 from the right. That's because the graph is not defined to the right of 4. So this limit does not exist since the left and right hand limits are not the same. Now here is another example of a function that has neither a right nor left hand limit as x approaches 0. This is the function y equals sine of 1 over x. As x gets closer and closer to 0, the reciprocal 1 over x is going to grow without bound and become larger and larger. Since we are dealing with sine, remember that sine values are always between -1 and 1 inclusive. So this is going to continue to cycle between -1 and 1 repeatedly, and there is no limit as x approaches 0. Now this shows an important limit that we'll see later on, and we can justify the answer here by our graph. The limit as theta approaches 0 of sine theta over theta is equal to 1 when theta is measured in radians. And as you can see from the graph, the left and right hand limits are both 1.